Hello there, my name's Gary Sims and this is Gary Explains. Now, I've done quite a few software projects here on this channel. I've made videos about them. I've done my own encryption algorithm. I've done my own real-time operating system called Piccolo OS for the Raspberry Pi Pico with context switching and all that kind of stuff. I've got Piccolo Basic, a basic interpreter for the basic programming language. And in this video, in fact, over the next two videos, I want to look at how you write your own database. Now, it's going to be a type of NoSQL database. In the first video, we're going to look at how you store that information in the memory so you can access it quickly. And in the second video, we're going to look at how you write it to a disk so that you can have good performance, backup, and when you reload it, it goes back into the memory and so on. So if you want to find out more, please let me explain. Okay, then part one, which is really about balanced binary trees. But before we go into that, let's just look at what type of database we're going to be building. As I've said, this is the first of two videos about writing your own database. It will be a key value database where you store a key and then a value for that key. So for example, you might have score and then 1, 2, 3, 4, username Gary, or this is a barcode. You might have a barcode and then you can store some more information like JSON. So it's telling you it's a product, multivitamins, a price, €4.99, dollars, whatever. You could even use a UUID, 128-bit UUID, and then you can have a value associated with that. You can store whatever you want, as long as you have a key, which is unique, and then a value which is not unique, and it could be a complex value like JSON. Now in part one, we'll talk about how you store the key value records in a balanced binary tree. And then in part two, we'll look at how you store that structure, that data structure, the balanced binary tree, on the disk. So that, of course, when you restart the database, the information is still there. I've named it KVDB Lite, so Key Value Database Lite, because it's only a few hundred lines of code. It keeps all of the data in RAM all the time, doesn't try to access the disk to get the data, and then you can save to the disk so that it can be reloaded at restart, and it's all written in C. Now, of course, what you want to be able to do is find your data quickly. Now, there are hundreds of ways of storing data both in memory and on disk. For example, you could just store it as a list. So you've got that list of keys and the list of values, and the problem is when you want to find something, you have to go through every item because you don't know where it is in the list. So it could be the first item. If you've got a million items, it could be the last one, and going through it serially one after the other will take a long time. And of course that won't scale at all if you were trying to write some kind of server that handled thousands, even millions of transactions, then that would definitely not work. So of course you could put it in a sorted list, which would make finding it easier, because if you're looking for, let's say, the key score, then once you find the key starting with T, then you know you've gone past score, so you don't have to go to the very end of the list. However, if you're still looking for like username or zoo or zoological, then you're still going to need to go from the beginning of the list to the end of the list. So again, not really very helpful. There are some ways of doing binary searches on lists where you could try to find it in the middle and then say, well, it's in the top half of the list because of where you are in terms of alphabetical sorting, and then you can kind of cut it down that way as well. That is really what a balanced binary tree is in many ways as well. Or you could use a binary tree which does that splitting in half for you automatically. That's the idea of a binary tree. There's a left and a right. It's a tree structure. Left is in one direction, right is in the other direction, up or down the list basically. So here is an example of a binary tree. These are some keys. So notice here it's all very nicely sorted. So you've got real name, okay, and then password. Well, P is alphabetically before R, E is before P. So if I were looking for email, I'd start here and say, well, E for email is going to be in this direction. I'd get to password. E is again in this direction, then I'd hit the email. Obviously, you'd have different branches in a much more complicated tree. If I was looking for verified, I would start at real name, V comes afterwards, so I'd go this way. Username, I'd go this way, I'd get to verify. So that's only one with 5 entries. You can have them with 1 million entries, splitting at each node. For example, if I had the word ultra in here, then I'd go to real name, username, then in fact I know I'm UL is to the left, and then I'd find ultra rather than going to the right where I'd find verify. So you can have that, and you can have this on a massive scale. Now the problem is when you want to insert something. So here I've got the word status, a key for a value that I want to put in there. A key value is status. Where do I put it? Well, it comes after S and it's before username. So do I put it in here? What's the best way to deal with that? In fact, this would be the best way to deal with it, that you slot it in there and then you have username afterwards and then ultra and verify. So the tree has grown now on the right hand side. However, that is not balanced. As you can see, this has now got 4 items on one side and just 2 items on the other side. So you'd want to balance this tree, otherwise it's going to end up lopsided. So in fact, this is the picture of the tree once you've balanced it, with 3 nodes on each side. Status is now the root, and again, if we were looking for ultra, we would go status. Well, U comes afterwards, go to username. UL comes before US, so we go to the left there. And now the tree is in a perfectly balanced form, which means that if we're looking for any word, we know we can get there in a short number of hops. Now the question is, how do you balance a tree like this? What are the techniques for creating a tree that is equally divided on the left and on the right at any point at any node? Well, there's a thing called an AVL tree, named after the inventors Adelson, Velsky, Landis, and it's a self-balancing binary tree. In an AVL tree, the height of the 2 child subtrees of any node may only differ by 1. If at any time they differ by more than that, then it has to be rebalanced to restore that balancing property. Grigori Adelson, Velsky and Evgeny Landis published an algorithm for the organization of information as a paper in 1962. It's the oldest self-balancing binary tree data structure that was invented. So it's called an AVL tree. It's a balanced binary tree. To keep the tree balanced, an AVL tree can perform rotations on part of the trees, and we'll talk about this in a moment. Left rotations and right rotations, and then of course there are also rules for insert and delete. So let's have a look at a left rotation. Here I've got 3 things. They're right in the right order: real name, status, username. Okay, but that's not balanced because it's all down to the right hand side. You really want a node in the middle and 2 underneath it. So you can balance this by taking this middle node and pushing it up, and taking this top node and pushing it down. That gives you this. So we've gone from real name is the root, and then a child of status and a child of username. We've pushed up status to be the root, and then real name has gone down the left hand side. So this is an up and a down. So that's a rotation to the left. If you can imagine those 2 arrows, that rotates it. If you go up on one side, down the other, it rotates to the left. So if we did that on our tree here, we could rotate this these 2 here, real name and status. We could push status up and real name down, and by doing that you then get this setup. So if you notice, we go back, look what's happened. So real name went down to be below status. Okay, so that's what it's done here. Real name has gone down to be below status. Okay, and status has gone up to be the root. Now you then attach on what was onto the left here to make it still in the right order, and to the right here. So this is almost balanced. It's not quite balanced because now we've got this long chain here on the left hand side that should also be a group of 3, and for that we do a rotation to the right. So a rotation to the right is exactly the same, just in the opposite direction. So we bring this one down and that one up. So this one down and that one up, so that makes it rotate to the right. Now the way you do that in code is very simple. If you've got these nodes, you've got pointers to them, let's say this is A, B and C, what you say is that A left, so this connection here, becomes what was either on B right, in this case nothing, and B right becomes whatever was in A. So you don't lose anything because what was in B right has already been moved, and B right becomes A, and then you return B as the top node. So you do that shift and you end up like that. So this is the basic steps. It's the other way around for the other rotation. So you just moving around connections, pointers to the different bits of information in your tree. It happens very quickly because you're just literally doing a quick shuffle here of the connections between the nodes. And if you've done that left shift and then that right shift, you end up with that balanced tree as I had shown you earlier on. Now the good news is, since this algorithm was published in the 60s, there are plenty of implementations in many languages, including C, C++, C#, Python, Java, Go, Rust, whatever you want. It's there. As long as you understand the principles as I've just shown you, that the tree is balanced, that to balance it you do it by rotations, then you don't need to reinvent the wheel. Just like today, there's lots of libraries for cryptography and for linked lists and for all kinds of dictionaries and all kinds of data structures, particularly in languages like Python or C++. You don't need to do it again, just use what's already there. Now in my code, basically we have this idea of a node, and there's a pointer to another node to the left, a pointer to another node to the right. There's the difference. Is it more than one node height difference? So we know we need to balance it or not. And then you have the key and the value. And inside the code, you're going to find rotate left, rotate right, and a balance function that go through and balance the tree at any time it's needed. So for example, here's the rotate code, rotate right. As we saw, literally, you pass in the node that you're going to rotate around, and then basically you set the left, set the right as I showed you, and then you fix the diffs. That means fixing this number here so that it reflects the correct height in the tree. Really quite simple. And then you return the root pointer, RP in this case, which was a double pointer, so you can just return it through the parameters. And then inside of the actual code itself, we've got an AVL tree itself, a structure for that. We've got functions for like doing a lookup. We've got functions for insert, remove, free, and so on. So these are the public facing functions that if you're writing another piece of code that uses KVDB Lite, you would use these functions that have been exposed so you can manipulate the tree by adding and removing keys, basically. Now, all of this code is available in my GitHub repository. There is the URL. Basically, it's got its own repository, KVDB Lite. Go and look at the code. Very simple. Just 3 files, I think, a header file, an example program, and then the actual KVDB Lite itself. So pretty easy. Just go and have a look. Okay, so in part 2, we're going to look at how you now save this structure to the disk. We're going to talk about, because this is a database, then that we're going to need some performance issues. So transactions are going to come in here because they help with performance. And then because obviously storing data is important, we're going to have to look at what happens if, you know, the computer crashes in the middle that you're writing to the database. What happens? Is there a recovery technique? Can the database, recover from a fatal error that happened right at the moment when you were doing something? I've tried to build that lot into the database so that it is as secure and as reliable as possible. Okay, so if you want to catch part 2 of this video, do make sure you subscribe to the channel so that you know when that video comes out. Okay, that's it. I'll see you in part 2.